Hi, I'm Kelvin. Welcome to my cave. Last time, we looked at a bunch of configurations for feedback amplifiers using op-amps. We studied the non-inverting configuration, which has an astonishingly high input impedance, a near-zero output impedance, and a gain that can range from 1 if the feedback path is a simple wire, to whatever gain greater than 1 that we like. We also tried transposing the inputs of the non-inverting amplifier and made an inverting amplifier. It had nowhere near as good an input impedance, but it could give us any arbitrary amount of negative gain. Both of these had the common property that the feedback path was a simple voltage divider. Now I'd like to start looking at the case where there are more interesting things in the feedback path. There's a way of thinking about this that I think might be helpful, that I call the monster in the feedback loop.
The idea here is that a great many circuits that involve feedback do essentially the same thing. There's a signal coming in that goes to one of the inputs of an op-amp. I'm showing a non-inverting configuration here, but you can think of it in much the same way with the inverting configuration. The op-amp's output goes through some sort of black box that does something to the signal, and the output of the black box goes back to the input of the op-amp in such a way that there's negative feedback. What's inside that black box can be almost anything as long as the feedback stays negative and we don't go outside the limits of what the op-amp can respond to. So far, the only feedback network we've looked at is a simple voltage divider. That gave us a way to get an output that's any linear function of the input signal. To get something interesting out of that circuit, we have to look at the op-amp's output, because the black box's output will be the same as the circuit's input, say the golden rules of op-amps. And the circuit's overall output is the inverse of what's in the black box. But we're not limited to a divider. We can put anything we please in that black box. If we have a slimy green monster in there, as long as what the monster does is predictable and stays within the rules of our op-amp will do the opposite. Our circuit, taken as a whole, becomes an inverse monster, whatever such a thing that might be. An anti-monster? A Retznom? The op-amp is still operational in terms of carrying out a mathematical operation. Here, the operation is inversion of a function. Let's take a look at a more interesting example, a diode in the feedback loop. The first question: does this circuit follow the golden rules? Well, sometimes. If the input voltage is negative, then the op-amp can output a positive voltage to make the currents balance. If the input voltage is positive, then there's no way for the currents to balance. The op-amp will swing all the way to the negative rail, and the diode will be cut off. There's no feedback. But okay, let's assume that we do always have a negative input voltage. What then? Well, the Shockley diode law tells us that the forward current in the diode will be approximately exponential in the voltage across it. And that current has to balance with the input current, which Ohm's law tells us is proportional to the input voltage. Putting these two facts together, and knowing that the monster in the feedback loop produces the inverse monster at the output, we get that the output should be approximately proportional to the logarithm of the input. Okay, that might be a little hand-wavy, but really, the circuit works. To do it more formally, we'll write out the second golden rule of op-amps. We'll substitute in the formula for the input current using Ohm's law, and we'll substitute in the formula for the feedback current through the diode using the Shockley diode law. We can solve for the output voltage in terms of the input on Algebra Autopilot. When we look at this equation, we might worry a little bit. A logarithm can be negative, but obviously the feedback current can't be. Well, we started with a simplified Shockley formula. There is actually a +1 in the argument to the logarithm, and the log of a number greater than 1 is always positive. But we should also look at what the argument of the logarithm is. The saturation current I sub s will typically be about a femtoampere, and R sub in this circuit is 10 kiloohms. The denominator here will be about 10 picovolts. So the log is going to be negative only if the input voltage is within about 10 picovolts of ground. We promised that the input voltage would always be negative, or rather, that we didn't care about saturating the op-amp if it went positive. If we're that close to ground, even thermal noise in the wires will push the input voltage negative. There's no problem here. The output voltage is proportional to the log of the input voltage. Let's see this in action. I drew a schematic of the circuit I want to test. As usual, it's on the project GitHub, linked down in the doobly-doo. The first op-amp is exactly the circuit we were just looking at. I'm going to feed it with a negative 10-volt ramp for my function generator. The output of the first stage is going to be only a diode drop at whatever current the diode is carrying, so at most 3/4 of a volt in this setup. The second op-amp stage is a non-inverting amplifier with a gain of 10 to bring the output into a nicer range for the scope display. I'll wire up the scope in XY mode, showing the output voltage as a function of the input. The two op-amps are on a single TL072 IC. I've laid the complete circuit out on the breadboard here. I'll hook up my function generator and scope, power everything on, and capture that XY display. If I invert the x-axis, the trace certainly looks like a graph of the log function. This circuit isn't a great logarithmic amplifier for many purposes. It's horribly temperature dependent, because the current through the diode will approximately double for every 10 degrees Celsius rise in temperature. There are much better log amps available. But back in the day, this circuit, often built with discrete components, was in practically every VU meter on a tape deck or mixer board, S meter on a radio receiver, and so on. Before silicon diodes, they were built with germanium ones, selenium ones, and even copper oxide rectifiers. The resistors in the circuit would be trimmed by hand to account for device variations. So now we've seen a couple of examples of admiring the monster. If the monster is a voltage divider, then the op-amp circuit becomes a voltage multiplier. If the monster is a diode and resistor, the op-amp circuit becomes a circuit that computes logarithms. We're going to see a lot of other circuits that admire the monster in the coming episodes. But there's another important thing that we can do with the monster in the loop. Sometimes the monster represents an effect that we don't want, but can't avoid. In that case, we can change things so that our circuit's output simply is taken from after the monster in the loop. If the other path was called admiring the monster, this one can be called hiding the monster. One important example is one that we see all the time in power circuits. We have some sort of voltage source that we want to deliver to a load that has a very small resistance. We need to deliver the power through a relatively long length of wire. Unfortunately, our wiring is not ideal. There's some resistance to it. If, say, that wire is 1 ohm and the load is 10 ohms, that's already a 10% error in the voltage we're delivering. And the voltage drop in the wire will depend on the applied voltage, the load, and the absolute temperature, so simply compensating for the voltage drop might not be possible. In 1861, Lord Kelvin, the same Lord Kelvin of thermodynamics fame, invented a clever way of controlling a remote voltage without worrying about voltage drop in the wiring. Even though he was using a Wheatstone bridge and manual adjustments, while we have the luxury of op-amps and feedback, the circuit is still called a Kelvin connection. Here's how it works. We'll connect a second wire directly to the load and run it back to our driver circuit. And our driver circuit will be an op-amp wired as a follower. If we recall our golden rules, the feedback loop will ensure that the voltage at the load is equal to the voltage at the source, provided that the op-amp can source enough current. But wait, won't the feedback wire also have a resistance, and won't that get in the way? Well, remember the other golden rule of op-amps, the inputs draw negligible current. That means the voltage drop in the feedback wire will also be negligible. We've hidden the monster of wiring resistance. Another important application of hiding the monster is when you have a circuit that distorts the signal and want to remove the distortion. Here's one example, a power amp to drive a speaker. There's a log taper pot to set the volume, and a feedback amp with an op-amp set for a gain of 10, R1 divided by R1 plus R2. There's a 2-transistor push-pull follower made of some fairly beefy power transistors, and an 8-ohm speaker. I found that I needed a compensation capacitor to keep the circuit from oscillating under the reactive load. The simple push-pull follower has a ton of crossover distortion, but the feedback loop makes the op-amp output compensate for it. If instead I were to move the resistor and take the feedback directly from the op-amp output, the op-amp output would faithfully mirror the input, but the speaker would give a distorted sound.
I've built the amp up on a breadboard here. I'll drive it with a sine wave. If I take the feedback from the op-amp output, what comes out of the speaker sounds sort of like a reed instrument. The scope trace from the speaker terminal shows the distortion, and the Fourier analysis shows a bunch of peaks at the harmonics. If I move the feedback connection to the speaker terminal, now the speaker output sounds more flute-like. And the scope trace shows less distortion and less power in the harmonics. By the way, this still isn't a great speaker amp. If you try a higher frequency input signal, some of the distortion will come back. I'll get around to covering more about power amps one of these days, including how to fix that problem. Now we've seen the two purposes of a nonlinear component in a feedback loop. Admiring the monster, that is, computing the inverse of whatever the nonlinear part does. Or hiding the monster, compensating for some unwanted effect in the circuit. Next time in this series, I'll fill in some material that we missed about how a single op-amp can subtract as well as add. Following that, there are a whole bunch of op-amp-based building blocks that I want to cover. Over in our other series, I wanted to make more progress on restoring my 50-year-old analog oscilloscope, look at overdriven differential pairs in the transistor course, and start making our triangle wave generator more versatile and controllable. So there's lots of material coming. I hope you'll stick around to watch some of that, and maybe ask the YouTube algorithm to tell you when the videos come out. In the meantime, stay safe, stay healthy, stay curious, and take care of one another. Bye!